Okay, it's on. So we're just getting ready to talk. Let me see, how does this work?
Okay, I think it makes sense to get started with the second.
Okay, now how do I do this again? How do I control it?
Well, I was called on Jack Sarfatti to talk about entanglement.
But Virginia, how do I control it? How do I
How
control
should I know? That's what Jennifer is for.
Jennifer, how do I control this? Oh, okay, so this goes, all right, should I start?
Yes.
Yeah, back to it. Okay, now some of you may have seen the new book by David Kaiser at MIT called How the Hippies Saved Physics, and in which I am a major character.
That you are a character we never doubted, sir.
Yes. But it says we helped start the quantum information revolution, quantum computers and cryptography and all that kind of stuff. And at the time, back in the 1970s, I had a crazy idea to try to use quantum entanglement as a standalone signaling device, which at that time it was not that well understood. Then the no cloning theorem came and various no signaling theorems came about, and the consensus of opinion, even my opinion, was that you cannot use quantum entanglement to send messages without a key, a classical signal key, to unlock the message that's encoded non-locally. But then, when I started reading David's book, David's an MIT physics professor, historian of physics, and he had a picture of one of my early crazy schemes. Nick Herbert also had some schemes that didn't work. And then I realized, well, maybe there is a loophole after all. So I'm going back to square one. I present to you a argument that you can signal with using entanglement without the classical key. And of course, if you do that, it opens up a big can of worms. It means all quantum cryptography, a lot of the assumptions people are making are questionable. And now, one of the features of the no signaling theorem is that you cannot distinguish non-orthogonal states. And but however, I don't know why they say that, because the lasers produce what are called Glauber states, and also they have squeeze Glauber states. But the Glauber states are eigenstates of the non-Hermitian photon destruction operator, and they're not orthogonal. And we could certainly distinguish different Glauber states. The Glauber states are the closest you get to like a classical wave quantum mechanically. They're minimum uncertainty wave packets in number and phase, and we can tell the difference between, the phase can be different, the average number, intensity can be different. We can certainly distinguish non-orthogonal states. So now let me get to the cut to the quick on this. To get to the key, I'm going to skip all this. This is from David Kaiser's book, How the Hippies Saved Physics. This is my original idea for communicating faster than light, figure 9.1 of Kaiser's book. Okay, now, there's a young man named Anthony Valentini, and he has written, it is argued that immense physical resources for non-local communication, espionage, that's why the CIA was very interested in all this stuff and funded us, exponentially fast computation are hidden from us by quantum noise, and that this noise is not fundamental but merely a property of an equilibrium state in which the universe happens to be at the present time. And they said non-equilibrium matter could be used to send instantaneous signals to violate the uncertainty principle, to distinguish non-orthogonal quantum states without disturbing them, to eavesdrop on quantum key distribution, and to outpace quantum computation. So obviously this is very important. If you can, okay, it's like extremely important. So let's go on, and I'll quickly, okay, now, here's a little toy model. What this is a entangled state, which alpha and beta are the sender states, and the 0 and 1 are the receiver states, but alpha and beta are the Glauber coherent states that lasers make. This is quantum optics, okay? And you can actually, you should be able to create such a state. Now, suppose you have such an entangled state. So the receiver is just one ordinary qubit. It could be a spin, but somehow is entangled with these two, with alpha and beta, two different coherent states. Alpha and beta are actually like complex numbers, in polar representation, amplitude and phase, sort of things. And I just did, this is the, just took the inner product and everything normalizes to 1, and that's, this is all elementary quantum mechanics. And now here's the condition. The condition for the inner product, for the bracket of 2 coherent states is this. It's not 0 when alpha is not equal to beta. It can quickly drop to 0 because of the exponential, okay, but it's not 0, so it's not a Dirac delta function. And then what you do, and this is very simple, this is the density matrix of the total entangled state, just the outer product, right? The ket bra, rather than the bracket in Dirac notation. So that's what it is. Now, how do you do quantum mechanics? How do you do the Born probability interpretation? Well, if you read Henry Stapp, using projection operators and density matrices, it's just a slightly different notation from elementary quantum mechanics. But what you do, you take the trace of the projection operator. Now, what is this? This is the this thing here. This is simply the I'm calculating the probability to measure a 1 at the receiver, of the qubit, just a 1 thing. So it's just the trace of the projection operator times the total density matrix. But here's the thing. See, if we were doing this, say, with the Aspe experiment, if you're doing just spin correlation measurements, okay, this alpha, that term there, alpha beta with respect to A. A is the sender. Alice is the sender. Bob is the receiver. Okay? In an ordinary orthogonal states, that term is 0. Okay? Here it's not 0. So that means that the probability to measure, say, a 1 at the receiver at Bob's position, depends upon the overlap of the coherent states at the sender. That normally everybody assumes that's 0. That's what they say. You can't distinguish non-orthogonal states. Who says you can't distinguish non-orthogonal states? Did you ever talk to a laser physicist? I don't know where these guys are coming from. What's going through their head? I mean, maybe I'm missing something. I'm not saying I'm right. If somebody here can point out my error, please do. But I'm saying here's a counterexample. Here's where you can communicate by entanglement and fascinate. In other words, what you get at Bob's receiver depends upon the way you set up the settings at Alice's sender. The way you can modulate that inner product. You can think of all different kinds of ways. You phase modulate, amplitude modulate. You can modulate the thing in time, so you're getting a signal. So that's basically the result. And I'd like somebody to shoot it down if they can. And I think I just now one other thing. There's one other very spooky thing about this. This is topological. The space-time difference. Okay, look, you're doing two things. When you send a message, when Alice sends a message, she's doing something irreversible. And when Bob detects the bit, he's doing something irreversible. Wheeler, no measurements, a measurement tool, it's an observed measurement, irreversible, amplification, all that kind of stuff, the measurement theory. So, but the point is, unless you've destroyed somehow the entanglement along the way, we're assuming that everything's protected, you don't destroy the entanglement along the way. In principle, Alice can send her message before Bob receives it, retrocausal. There's nothing here. It doesn't. They could send it simultaneously. They could send it time-like, space-like, light-like, whatever you want. It doesn't. It's like a topological information sort of thing.
In that case, you stopped talking 2 minutes ago.
Okay, I'm done. So that's basically. So it's very peculiar what's going on. There's probably a mistake, but where is the error? I'm not.